Hello and welcome back to the third geostatistics course with QGIS and R. The main topic of this course is structural analysis for Kriging Cokriging interpolation. This is the 8th lesson of the course and today we are going to be talking about cross-validation. Let's start with a very short summary about what we did at the previous lessons. On the second lesson, we learned how to create the omnidirectional semi-variogram cloud. On the third lesson, we learned how to create the directional semi-variogram cloud. And here we have an example for a direction of 30 degrees. Later, in lesson 4th, we learned how to pass from the omnidirectional semi-variogram cloud to the omnidirectional experimental semi-variogram, and also from the directional semi-variogram cloud to the directional experimental semi-variogram. Then, on lesson 5th, we learned how to fit the theoretical semi-variogram model on the experimental semi-variogram for a omnidirectional one and also for a directional one. On lesson 6, we was talking about isotropy and anisotropy and how we can characterize the anisotropy of the data using the variogram map and also the experimental semi-variogram in different directions. On the lesson 7th, we learned that if we want to deal with anisotropy, we have to use a specific model. We can no longer use the regular model that we was using for the omnidirectional experimental semi-variogram. We have to use theoretical models that are specific for geometric or zonal anisotropy. Now, in this lesson number 8, it's time to see how we can validate the model that we fit on the data. To do that one, we are going to use the cross-validation. The cross-validation is a very powerful tool that is going to help us to quantify numerically how good is our model. Also, with the parameters that we are going to get from the cross-validation, we can perform different graphs that are going to be pretty useful to have a better understanding about the model. The cross-validation is using the Kriging interpolation to estimate the value of a parameter in those locations where we have already a sample or measurement. Then it's making the comparison between the real value and the estimated value, and the difference is the error. As bigger is the difference, bigger is going to be the error. The two more popular types of cross-validation is leave one out cross-validation and key-fold cross-validation. Let's go to see the first one. Leave one out cross-validation. An observation, this observation could be a value of a sample or a value of a measurement, is removed and the model is fed in the remaining data, and this feed is used to predict the value of the deleted observation. This is repeated n times for each of the n observations. Let's go to see how it works with the Meuse River dataset. Then we have all these dataset. In total there are 155 samples, okay? Then what we are going to do first is remove one sample, for example this one. And then with the rest of the samples, we are going to predict this value. But this value is going to be predicted with the model. It means that we are going to use this model over here, okay? And we know that this model has a range, and with this range, we know what is the correlated area and what is the uncorrelated area. Then we're going to use just the values that are related with the correlated area, okay? For example, in this case, if the range is 900 meters, we have to know that to predict this value over here, we are going to have a distance from here to here that is going to be 900 meters. Then all the points inside this range are going to be used to predict this value. then this value, the predicted value from this point, is going to be compared with the real value, the observed value. Then the differences between the predicted value with the observed value is going to be the residual. And that one is going to be for fold 1. Then we are going to do the same for fold 2. We are going to remove this value, and with the rest of the values according to the model, then we are going to predict the value over here. Then again we are going to compare the predicted value here with the real value, and we are going to do that one for all the samples. In this case, then we are going to have 155 folds, because we are going to do the same for all the samples in all the locations. The other method is the cross-validation K-fold. The K-fold method performs exact K-fold cross-validation. First, the data are randomly partitioned into K subsets of equal size, or as close to equal as possible, or the user can specify the false argument to determine the partitioning. Then, the model is refit K times, each time leaving out one of the K subsets. If K is equal to the total number of observations in the data, then the K-fold cross-validation is equivalent to the exact leave one out cross-validation. Now let's go to see how this method works with the Meuse River dataset. Let's go to imagine that we have, for example, 150 samples, and we decide that we want 10 folds. Then we are going to divide 150 between 10, and then for each fold we are going to have 15 samples. That samples for each fold are going to be taken randomly, and the samples for each fold are unique. It means that if in fold 1 we have this sample is not going to be in another different fold, okay? Each fold has different samples, okay? Then for the fold 1, the software is going to remove the values of all these 15 samples, and then it's going to use the rest of the samples to predict the value in those locations where we remove it, okay? And it's going to predict these values according to the model that we created. Then we are going to have for each of these locations the predicted value according to this methodology and using the model, and also the observed value. Then the differences between the predicted value and the observed values is going to be the residual values, and we are going to do that one for the 10 folds. Then at the end, what we are going to have is 150 values that are going to be the predicted values, and 150 observed values that are going to be the real values. Then we can make the differences between them, and then we are going to have the residual values for all the data set. Now let's go to create the first script. Go here, click create new script, and I'm going to paste what I did already. I'm going to make this windows bigger, and the first script is going to be the number 35, and it's going to be the leave one out cross validation, and it's going to be for the omnidirectional model, and we are going to create a table with different parameters. Now we are going to see the parameters, okay? Then I'm going to cut this one here and save with that name. Save over here, paste, save. Also, I would like to remove these two lines over here, and let's go to talk a little bit about this script. We already know about all this stuff, but let's go to make a summary. This is for the name of the group that we want to save the information. Is going to be in structural analysis. It means this one over here. If we go to R here, we're going to see that there is a section that says structural analysis, okay? That's because we put this name over here, okay? Then this 9 is something new, and we have to put this one over here when we are working with the cross validation. Okay, that's important because we are going to use the RGDAL. Okay, also this one is for the layer that we are going to use. This one is for the parameter that is inside this layer, and all these ones is related with the experimental semi-variogram and also with the model that we are going to use. And this one is to create a table. Okay, then we are going to use the library that is gstat, and this one is to define the model that we are going to use. As you can see, I added 4 different models, but could be even more models. In gstats you can check gstats, there are a lot of different models, but the most popular are going to say is these 3 one. Okay, the exponential, the spherical, and the Gaussian. This one is to define the parameter that we are going to use as a numerical one. This one is for the experimental semi-variogram. As you can see over here, we are assuming that the data is covering at least the intrinsic hypothesis for the stationarity. And this one is for fitting the model on the experimental semi-variogram. In this case, as I said, is for the omnidirectional one, because we didn't add here any specific direction. Okay, and this one is the script for the cross validation. As you can see here, cross validation, and here we are saying that the data is stationary. We are adding here what is the layer with the information and what model we are going to use. As you can see, we are using this model, and this model is this one here. Okay, and as you can see, here is the experimental semi-variogram. This one over here, the same information as here, and also here we added the model. For this kind of a script, we are using the fit automatically. Okay, we are going to do a different script where we are fitting the model manually, and the results for the table are going to be different. Okay, but in this case is for fitting the model automatically. And also with this line over here, we are going to export the information in an spreadsheet. Also, I added all this information here to print the information in the screen. Also, we are going to have the information in a spreadsheet, but also we are going to see the information printed at the screen. And one important thing also related with the cross-validation is the argument associated with the type of cross-validation we are going to do. If we don't add it here, the number of folds that we are going to do, by default, the software is going to assume that we are going to do the leave one out cross-validation. Okay, we are going to see later a different script for the KFold. Now let's go to run that script and see what kind of information it provides us. Then let's go here, structural analysis is number 35, leave one out cross-validation, double click to open, and the parameter that the layer is loaded automatically because there is just one shapefile here. Then the parameter is going to be the logarithmic with base 10 for the zinc concentration. Cutoff, we was talking about all these parameters already. I'm going to use 1500 meters. Lag distance is going to be 100 meters. The partial seal, this is the values associated with the model. As I said previously, the model is going to be fit automatically. Then we have to add values that are approximately. The model, we are going to use the spherical one, but you can do the cross-validation for any of these models and see what is the results, right? Then the range, again, is approximately. I'm going to add 1000 meters. The nugget, I'm going to add 0.01. Again, it's approximately, and we are going to save the spreadsheet. Okay, then save to the file, and I'm going to save in this folder, and make sure you have this one selected here. Okay, And this name is good, but no, maybe I'm going to add here, leave one out, cross validation, omnidirectional. Okay, I'm not going to leave any space. Save and run. And as you can see, we have a table loaded over here. Let's go to open this table. And let's see what we have here. The first column is for the number of sample. The second column is for the predicted value with the Kriging interpolation. The third column is related with the variance. Then the fourth column is related with the observed value. That is the real value, is the value we have on the samples. Then the residual is the differences between the observed and the predicted value. Then we have the set score. This value is related with the residual value divided by the standard deviation. Here we have the number of faults. We are going to have 155 faults because we have 155 samples, and now we are using the leave one out cross validation. Here we have the coordinates, and here we have optional. That is true. I don't know. I'm not sure what is this column about it. And that's the values we have in these tables. Okay. Also, I'm going to close this one. If we go to the folder, this one, we have here the spreadsheet. Let me open. Okay, open as a copy, and here we have the same values, but here we can manipulate this table to have different graphs, whatever you want to do with an spreadsheet. In this case, I'm using OpenOffice, but you can use the Excel from Office. But just to let you know that OpenOffice is a free and open source software. Then we can close this one here, and also we can see the information that we have screen, print screen, we can see over here, and also we can open from here. And here we have the same information as I showed you at the table, right? We have the predicted values, the variance, the observed, the residual, set a score, and the number of faults. But also we have here we have the model. Okay, the model is saying that we have the partial seal for the nugget effect is this one, and the partial seal for the model is this one. We have the spherical model, and we have the range over here. Also, we have different statistics associated with the parameters. For example, for the predicted value, we have the minimum value, we have the first quantile, the median, the mean over here, the third quantile, and also the maximum value. And we have all these values for all these parameters showing here at the table. Then we have the same information here, okay? In this screen, we have the same information as we saw over here. But maybe here it's a little bit better organized. I'm not sure. Okay, another important thing is if we go here to Google and let's go to look for Kriging cross validation. This one, for example, here we can see other things that we can use on the script, and it's interesting that we can use the minimum and maximum value for the local observations. Okay, as I explained previously, when we are doing this cross validation, instead to use all the points according to the model, we can say that we can use, for example, just 50 points, okay? Sometimes the computational time to do this kind of cross-validation is taking a lot of time if we have a lot of data. Then, for example, if you have a range of 900 meters, and for that kind of range you have 1,000 of points, maybe you want to reduce the number of points to have less time on the computation. Then you can specify that one here at the script, edit script here. Let's go to make this one bigger. You can specify here how many neighbors you want to use to do the cross validation, and that's the information that we can see here, right? And the argument, you can see the argument over here, here for the cross validation, okay, is this one over here. You can put, for example, I want a maximum of 40 observations to predict the value in a specific location, okay? And as you can see also here, the argument of n false is for the KFold cross validation, okay, as I said previously. Then you can use that arguments in the script to reduce the time of the computation. Now let's go to see what the residual value, this value over here, for this column, the residual value means for us, okay? Then let's go to look for the maximum differences between the observed value, that is the real value, and the predicted value. Then for the maximum residual is going to be 0.630, okay? And the predicted value in this case is, residual maximum here, the predicted value is 2.39. And here we have the coordinates for this location, X and Y. And now I prepare a spreadsheet with that information, okay? We have the observed value, that is 3.025, and it is this value over here, 3.025, that's the real value. Then we have the predicted value, is this value. This value is from the model. We get this value from the model. Remember that when we are doing leave one out cross validation, we remove one value, that is the real value, and then we calculated the predicted value with the model, and this one is the result. And this value 2.39 is this value over here, 2.39. Then, as you already know, what we have here is the logarithmic with base 10 for the zinc concentration in ppm. Then if we remove the transformation with this formula over here, 10 to the power of this value, we are going to get the real value for the concentration and for the zinc concentration in ppm. Okay, in this case the real value is 1059. Okay, and the value that we are going to get from the model is 247. And what we can see here is that the model under predict the real value because it's too much small compared with the real value. Then the differences between this value and this value is this value over here. And it is interesting to see that when we want to calculate the difference between these two values, we are using the zinc concentration in ppm. We are not using the logarithmic with base 10 the zinc concentration, right? Because if we remove the transformation of this value, that is the difference of these two values, okay, what we are going to get is this value, but this value is not real, okay? The real value for the difference is this value over here, and that's a very important point. Then when we want to calculate the difference, we have to use the real value, not the transform values. You have to be aware that I took the worst scenario, the worst location in the model, because that's the highest value for the residuals. If you check here at the table, we are going to see that the highest values are the first three values over here, and then the value is getting down, right? And we are going to come later to analyze all this information with different graphs and also different information that is going to help us to understand better what is going on with the model. But at the moment, I'm going to leave this information here, and then we are going to come back. Now, what I'm going to see is the next script. Then we can close this window here, new script. In this case is going to be the, let me make this one bigger, the NFold cross validation, okay, or KFold cross validation. Let's go to put KFold, better. KFold cross validation. And the script is more or less the same. We have the same information here, we have the same information here. Sorry, here I added this information that is related with the number of folds we want, okay, the cross validation, and that information is what we add here. You see this one over here, this argument. Then with this argument we can specify how many folds we want for the cross validation. Remember that the leave one out cross validation, we was removing each time just one sample. In this case, we are going to remove a group of samples, depending on the number of folds we want. But for the rest of the things, is totally the same as the other script. Then let's go to cut this one here. We are going to create also a table this time. Remove these two lines, and I'm going to save with that name. Then paste, save, and close. And now we can run the script. Then go to here, structural analysis is number 36. This one over here, double click. Parameter is going to be the logarithmic zinc concentration with base 10. This one is 1500. For the lag distance 100. Partial seal, it's something approximately because the fit is going to be automatically. And then I'm going to add 0.1. The model is going to be the spherical one. The range 1000. Nugget effect is going to be 0.01. And the number of folds, I'm going to select 15 or maybe 10. Then the data set is going to be divided by 10. Then we are going to save in a folder. The spreadsheet is going to be this one, but it's going to be the KFold. Then KFold cross validation, save and run. Then we have the new table over here. We can open this one, and the difference here, as you can see, is the number of folds. Okay, then we have, for example, all these samples are from the fold number 1, as you can see over here. Then the samples from here to here to 38 are from the fold number 10, okay, and etc. In this lesson, we are not going to discuss what is the best type of cross-validation. It depends on your data, and also it's not the scope of this lesson. But what I can say that the computational, in this case, as we don't have too much samples, for both methods it takes more or less the same time. And also the results for both of them are pretty similar. Let me show you what is the maximum value for the residual. As you can see here, for the maximum value, what we have is 0.631, okay? But for the other method, the maximum value, open attribute table, residual, is 0.63, okay? It's almost the same value. 0.63, 19, and the next decimal for the other one, 6309, okay? It's pretty similar. Now let's go to see the next script. I'm going to close this one here, close, and also close this one, and I'm going to paste what I did already, paste. In this case, with this script, we can calculate the leave one out cross validation, and we are going to have also the table. And in this case, it's for the omnidirectional model, but it's a manual one, okay? In this case, what happened is that the model is not going to be fed automatically is going to be fed manually. Okay, we have to provide the exactly values we want for the model. Remember that if you are not agree with the automatic fit, you can fit the model manually. Okay, and in this case we can use the cross validation for that model. Then I'm going to cut this one here. We cannot cover all the possible scenarios related with the cross validation, but I'm going to provide some of the scripts that you can use. But as you know, the number of possible scenarios is unlimited, okay? But I'm going to make some scripts with different options. This one is going to be number 37, save and close. We are not going to run that script, but just to let you know that you have to put the values for the partial seal, for the range, and for the nugget, the exactly numbers you want, okay? Then close. Let's move on to the next script, create a new script, paste. In this case, what we have, let me make this one bigger. It's number 38, and it's going to be again the leave one out cross validation. It's going to be a table also, but in this case is when we want to deal with universal Kriging, okay? In this case, with this cross validation, it is assuming that we remove the first order trained surface from our data. Then if you have that scenario, you can use this type of cross validation, okay? Then here for the formula, as you can see, is related with the universal Kriging, where X and Y is the independent variables and Z is the dependent variable, that is the zinc concentration. The rest of the things are pretty similar. Then we can cut this one here, cut and remove. Then, for example, if you want to have this script for the KFoldCV, what you have to do is just change the argument over here, right? Add the argument for KFoldCV, in this case is nfold, and then you have that option, okay? Then save, paste, and save. We are not going to run also this script. Then close, and let's move on to the next one. And this one is for the cross validation when we are dealing with geometric anisotropy, okay? In this case, as you can see, the formula over here is when we are assuming that the data is stationary, it's covering at least the intrinsic hypothesis, okay? Then if you are dealing with geometric anisotropy and you want to do the cross validation, you can use this script. Then the things are changing here is the variogram, the type of variogram, because we have to add the direction of the variograms, also the tolerance angle, and for the model we have to add the main direction of the anisotropy and the ratio, okay, between the two axes. Then we are going to save with this name. This one is also to create a table. Then cut this one, remove the two lines, and save, paste, save, and close. And the last one related with the tables is going to be for the zonal anisotropy. Then this one also has specific things related with the model, as you can see over here. Then let's go to cut, remove these two lines, and save. And now we can move to a different type of script. Then save and close. Now we have, I believe, 5 or 6 scripts related to the creation of tables with the values of the residual values and predicted values and etc. Let me double check. It's not this one, it's at the structural analysis. You see, we have from 35 to 40. We have 1, 2, 3, 4, 5, 6 scripts related with the cross validation to create a table, okay? Now, with the next script, we are going to create several graphs. I'm going to show you now. Make this one bigger. And we are going to save that one as a leave one out cross validation for the omnidirectional model and graphs. Okay, then I'm going to cut this one here, save over here with number 41, paste, save. And as you can see, this script has a lot of lines because we are going to create 4 different graphs. It's better, I believe, to run the script and see the graphs, but as you can see, we have a histogram for the residuals, we have a QQ plot for the residuals, also we have a bubble map for the residuals, and we have a scatter plot for the observed versus the predicted values, plus the regression line. That's all the graphs that we are going to create. And also we are going to get some interesting stats related with the parameters. Also we can add a title for the graph. And we are going to print also the values for the model. I believe it's better just to run this script and to see what we can get here. Then save. And let's go to run. For this one, you know, we are going to feed the model automatically. Then we have to provide the values approximately, okay? Then close this one here. Go here, structural analysis, and 41. This one over here, double click to open. Parameter is going to be the logarithmic with base 10 zinc concentration. Cutoff as usual. Lag distance 100 meters. This value is just approximately 0.1. The model, the spherical one, the range 1000. The nugget effect 0.01. The number of bins, that's for the histogram. We are going to add here 11 bins. The title of the graph is going to be leave one out cross validation. And that's it. We are not going to save anything. Then run. And double click to open. This one. And that's the graph we get. As I said previously, the bubble map for the residuals, the QQ plot for the residuals, the histogram for the residuals, and here we have a scatter plot that plot the observed values against the predicted values. Also, if we go back and see the values over here, we can see that we have the model, that the nugget effect is 0.011. Also, for the partial seal for the spherical model, we have 0.111. And for the range, in this case, we have 942 meters. Also, we have here a series of values for different parameters. In this course, we are going to be focused just in the root mean square error. And we are going to consider that the model that provides the minimum root mean square error, it means the model that the value is close to 0, is going to be the best model for us. Then we are going to try different scenarios. For example, we can try first with the omnidirectional experimental semi-variogram, then we can create the model, then make the cross-validation and see what is the root mean square error. Then we can do the same for the geometric anisotropy. For example, if we have anisotropy, and see what is the root mean square error, then maybe we can decide what model is the best. Then maybe if we decide is the omnidirectional experimental semi-variogram, maybe is the best. Then we can try for fit the model manually. You know, every scenario is going to be different, and every scenario is going to provide a different root mean square error. Then what we want is to minimize this error, and the model that provides the minimum value for the root mean square error at the moment for us is going to be the best model. I know there are a lot of different parameters, but I don't want to overcomplicate this course, and just I want to be focused on the root mean square error. Later we are going to talk a little bit more about this parameter. Now let's see what kind of information provide each graph. First, let's go to start with the bubble map, and here at the legend what we have is the residual values. For a pink one, it's a negative values, and for a green one, it's positive values. Remember that the residuals is these values here at the table. Open the attribute table. Is this column over here, and is the difference between the observed values and the predicted value by the model. And here we have the maximum value, that is 0.63, and that's the value that we can see over here, 0.63. Remember that for a positive number, what we have is the model underestimate, and for a negative number, the model is overestimate. And this one is really good because we can see the locations where we have the highest and the minimum values, okay? And as you can see in this area over here is where we have the maximum value for the residuals. Then we have to understand that these values, as they are the highest one, are making our model less efficient. Then maybe we can go and check what's going on with these samples over here. Why the predicted values compared with the observed values make that big difference, okay? Because maybe it could be something wrong with the sample. Maybe the day that was taking the samples, these three samples, was a different day that the day was taking the other samples. Or maybe these three samples are in a different geological unit, right? Or maybe these three samples were sent to different lab. Could be a lot of different things. Then we have to identify why we have these big values here related with the residuals. And we can identify these samples on the map. If we go here, then we can open this table here, for example. Open attribute table. Then the maximum value for the residual is this one with these coordinates. Then we can open the attribute table here for the shape file. Let me move this one over here, bring this one again here. I'm going to close this one, and open here the attribute table for the shape file. Let's go to minimize this one, and let's go to look for that coordinates. Then going to bring this one here also, and is the coordinates for this one is for the X 179470, then 1794 is this one over here, 179417, 331125, 331125. Then, as we know is this point over here, we can select this one here and look here at the map where it's located, and is this sample over here. A different way to identify where is located the sample is using the logarithmic with base 10 for the zinc concentration. Then open the attribute table, filter this value. Then here at the top we are going to have the highest value. Now we have to look for the value we are interested in, is this one, 3.025. then we can select this value over here, click over here, and then the sample is going to be selected on the map, as you can see over here. And this sample over here has to be pretty different compared with the rest of the samples over here. And that's because we have that big gap on the observed value with the predicted value, right? If we select here the information and we click on this one, we are going to get the values over here, and we can see that the zinc concentration in that point is 1060. And if we compare with the rest, the neighbors of the samples, you know, around this sample over here, we are going to see that in this case the zinc concentration is 140 ppm. Then if we move to this one over here, we have 241, and this one, for example, we have 801, and this one 784, and this one over here, for example, we have 186, and this one over here 226, and this one over here 119. Then what we can see is here we have the highest values, right? But here there is big gap between this one and these samples over here, and that's the reason, because in this case the model is not really efficient with this sample over here. Then we have to make an investigation and see what's going on with this sample over here. If we can remove that sample, or maybe we can treat the sample in a different way, because we can consider that this sample is a spatial outlier. Because if we compare the values over here and over here with this sample, it's pretty different. With these ones, the difference is not that much, because what we have here is 784, okay? It's not that big the difference, but for the other ones over here, it is really big. We have to know that to have spatial outliers in our data set is not something bad, okay? The first thing that we have to do is check what's going on with this sample. Why is the difference between this value and the rest of the values? And if we consider that the sample was well taken, or if the sample was the measurement was good, then we have to look for the reason. And maybe the reason is because here there is a former contamination, or maybe the reason is because here is the focus of the contamination. Could be a lot of different scenarios, right? And the important thing is to know what happened with that sample there, because in this case, from my point of view, what happened is that there is not too much samples in this area, and that's the reason of the gap. As you can see, the density of the samples here is quite big. Also here we have a lot of samples, but in all this area we don't have samples. And I believe that's the reason, because in this specific case, the model in that area it's not so efficient. It's something related with the number of samples taken in this area, because as far as I know, this project, the sample campaign was really well executed, okay? There is no problems with the samples are very trustworthy, but sometimes the samples are not good and there is something wrong with the samples. Maybe the instrument that we was using at the field to measure a specific parameter, the calibration of the instrument was not good, or maybe we was using different instrument to measure this sample over here and measure this sample over here, and we have to know all these things, right? Because if that happens, if the sample is not good, we have to remove that sample from the data set, because it's making our model wrong. Then we have to make sure that the samples that we are using to create the model, they are good. And if the samples are good, they cannot be removed from the model. Then we have to keep those outliers, even if they are making our model less efficient, because the samples are really important and they are indicating something. Okay, now let's go to move on to the next graph. That is a QQ plot related with the residual values. Then the QQ plot is going to help us to identify if the residual values are following a normal distribution. Also, the histogram is giving us that kind of information. At the QQ plot, what we can see here is at the tail, is these three values over here and these three values over here. At the tail, they are out of the line. If all the points are on the line, it is indicating that the distribution of the residual values are following a Gaussian distribution, a normal distribution, okay? But it's pretty normal that at the tail is these points over here, the tails of the histogram is these areas over here. It's pretty normal to be outside. And here what we can see is most of the points are pretty close to the line, and that's good, and it's indicating that the distribution of the data is pretty normal. And it's interesting to see the correlation between these two graphs, right? Because these 3 points over here are associated with the highest values for the residuals, and they are these 3 circles over here. And also this information is linked with the histogram. And we can see that these 3 points over here are going to be these 3 samples over here, where the values are higher than 0.5. Here at the histogram, we have the residual values here, and here we have the number of samples. And what we can see is the majority of the samples, a number bigger than 40 samples, the values for the residuals are very close to 0. And that's what we want, right? What we want is that the difference between the observed value with the predicted value to be close to 0. That is indicating that our model is really good. Then what we want to have is all the samples to be closer as possible to 0. Then if that happens, we are going to have all the values over here. And the distribution is going to be very short because the values are going to be all accumulated in this area. But as you can see, in this case, we have some values that are close to 0.5. They are not too much because here we have 10 samples, and maybe the samples over here is going to be 3 samples. And also over here, we have 3 samples that are pretty far away from 0. And is these 3 samples over here, and it is these 3 B circles over here. But in general, we can say that the distribution of the residuals, it's pretty normal. They are following a Gaussian distribution. The last graph is an scatter plot where we plot the predicted value against the observed value. Also, we have a red line where the origin is 0. And it's making an angle of 45 degrees with respect to the x-axis. Then, if we have the same value for the predicted and the observed value, what we are going to have is all the blue points on the red line. And that one is going to indicate that the difference between the predicted and observed value is 0. And in this case, the model is perfect. Because if the difference between the residual value and the observed value is 0, it means that there is no difference between the reality and the model we created. But as you are longer know, that is not going to happen. Always is going to be a deviation. Then that deviation is going to be the regression line. This regression line is the black line. Then, as we know that the predicted value and the observed value are not going to be the same, we want to create a regression line to see what is the difference between the ideal X scenario, that is the red line, with the real X scenario, that is the black line. And as closer are these 2 lines, better is going to be the model. But also we have to be aware that what we need is our data to follow a linear correlation, and also what we don't want to have is the blue dots to be very dispersed. We want to have all the blue dots on the same cloud of points. We don't want to have different cloud of points. In this graph also we can see the same information that we are seeing in the other graphs. These 3 points over here are these 3 points over here, are these 3 points over here, and are these 3 B circles over here. And these 3 values over here are the values that we say that they are maybe spatial outliers. And also is these 3 values over here. Let me make this one bigger. No, this one, the other one. This table over here, the 3 biggest values for the residuals are this one, and this one. And even we are saying that these 3 values are spatial outliers. They are at the same cloud of points, right? They are not really separated. And also they are indicating that these 3 points are part of the same population of the rest of the points, because they are not making a separated cloud of points. And that's something that we have to consider in this case. Now let's go to see a couple of slides I created. The first one is this one, to make a comparison between the ideal scenario where the observed values and the predicted values are the same. Then all the dots from our data are going to be on the red line. Then the black line and the red line are going to be together, and that's the ideal scenario. But most of the time what we are going to have is something like that, right? Where we have the ideal scenario with the red line, but we have the dots, they are not on the red line. Then we make the regression line, and we are going to see that the black line, that in this case is a blue line, okay, it is not exactly located as at the red line, but in this case is not that bad, right? And that's what we can see in this graph over here. The black line is quite close to the red line. Then this model, it's not bad, it's really good. And the other slide, it's an example about a really bad scenario. Here we have all these points that are making our regression line to be moved to this area. Because if we remove all these points over here, the regression line is going to be based in this cloud of points, and it's not going to be really far away from the red line. They are going to have pretty similar location, but because of these points over here, our model is really bad. Then we have to investigate what's going on with these samples over here, because these samples are making our model to be really bad, and maybe we can remove these samples to have a better model. Then we have to make a study related with the outliers. As I said previously, we want to see what's going on with these samples. We can remove these samples from our model. That's the question, in order to have a better model. And that's something that we have to look for information related with those samples to improve our model. In this case, looks like we have 2 different cloud of points, and maybe even they could be the same parameter or the same type of contamination, but maybe they are different populations, because maybe they are different events. Could be the same type of contaminant, but different events. And now we are trying to put these 2 events together and try to treat the information all together. And maybe that one is wrong. Maybe we have to separate these 2 populations and treat that one separately in order to have a better model. That's all the things you have to think about it. Okay, now let's go to move on to the next thing. How we can calculate the root mean square error. That's pretty easy. The P is the predicted value and the O is the observed value. Then we have to make the difference, square that difference, and then make the summation of all the samples. Then that one is going to be divided by the total number of samples. Then we have to do the root square. And that's the way we can calculate the root mean square error. Now let's go to see how we can make different models and compare this parameter. Then the first model is this one, that we decided to use the omnidirectional experimental semivariogram. Then we created the model, and the model is an spherical one. And for this model, the root mean square error is this one, 0.1722, and that's what I put over here. The model is the spherical model for the omnidirectional experimental semivariogram, and the root mean square error is 0.1722. And now I'm going to do the same for the exponential model. How we can do that one? Pretty easy. Go here, and change the model over here for the experimental one, for the exponential model. Then select here and run the script. And what value we get is this value over here. Then copy and paste here on the table. For the exponential, we have this one. Then going to paste over here. Control C, Control V. And now I'm going to do the same for the Gaussian model. Then I go here, and what I have to do is change this one, Gaussian model. Then run. And we have to be aware that when we change the model, all these parameters change, right? The nugget, the partial seal, and the range. In this case, what we have for the root mean square error is this value over here. Then copy, go here and paste over here. Then I'm going to show you here how the range also and the partial seal and the nugget effect change for the exponential model. Here we have these values. And in this case, what we can see here in this spreadsheet, that all the models are pretty similar. They are not making really big difference, right? Maybe the best is the exponential one, but there is no big difference between them. Later, we can check also the directional experimental semivariogram with the geometric anisotropy and see what is the result for the root mean square error. But first, let's go to see more scripts. The next script I'm going to show you, I'm going to close this one, is this script that is the same, but in this case, what we are going to get is the graph associated with the omnidirectional model, okay? But where we can fit the model manually, okay? Then I'm going to cut this one here and remove these two lines and save with that name. We are now going to run this script, save and close. Let's go to see the next one. In this case, it's going to be number 43, and is again the same script to create the graphs, but in this case, it's when we are using the universal Kriging, right? When we remove the first order trend surface and we want to calculate the leave one out cross validation, and then we are going to perform different graphs to see the results, and it's going to be this script. I'm now going to run also this one, cut, remove these two lines and save. And now let's see the next one. In this case, it's going to be to create the graph for the zonal anisotropy. Then in this case, we are taking in consideration a specific direction, okay? Then I'm going to save this graph. It's going to be number 44, geometric anisotropy graph, and in this case is for a assuming that there is no trend in our data, as you can see the formula here. But as I said previously, you can modify the formula to have different script, right? If you want to use this one for a universal Kriging, you have to change the parameters here. We explained already how to do that one in a previous lesson, okay? Then save with that name and save, and we can run this script. Close is going to be number, okay, I'm going to close this one. Structural analysis number 44. This one, double click, and let's go to field information. Parameter is going to be logarithmic zinc concentration. Cutoff is going to be 1500. Lag distance 100 meters. Again, in this script, the model is fit automatically. It doesn't happen for the sonar anisotropy, but for the geometric anisotropy, we can fit automatically. Also, you can change the script if you want to fit the model manually, okay? But we cannot cover all the scenarios. It is too much. 0.1, you know already how to do it. Let's go to start with the spherical model. The range is approximately 1000 meters. Negative effect also approximately. Tolerance angle, we are going to use here 22.5. As I said previously, you can use here for the tolerance angle 45 degrees. The experimental semi-variogram is going to be better because it's going to capture more points. The minor angle is 30 degrees and the major angle is orthogonal to the 30 degrees. Remember that 30 degrees is the direction of maximum anisotropy, and the orthogonal angle is going to be 120. Is 30 plus 90, okay, 120. Then the main direction, as I said, is 30 degrees. And now let me check the radio because I don't remember. It was 0.69. And the number of beans, 11 beans is good. And the title of the graph in this case could be leave one out, leave one out, cross validation, and in this case is geometric anisotropy. Then we can run this one and we can see the results over here. That's the graph. We have the outliers over here and also over here. We have the same over here and more or less the same over here, as we saw for the omnidirectional model. And the root mean square error in this case is 0.1729. Control C, and I'm going to paste over here. Control C, Control V. I'm going to put at the center. And as you can see over here is a spherical model, geometric anisotropy, okay? Now we are going to do the same for the exponential and for the Gaussian model. That's pretty easy. The only thing we have to change here is the model, okay? Now we want the exponential. Then run the script again. Then copy the value for the root mean square error is this one over here. Copy and going to paste in this table over here. Control C, Control V. And in this case, for the exponential one, is the minimum one. Is the one that provides the minimum error. That's interesting, right? Then the next one is going to be the Gaussian model. Then here, change for the Gaussian and run. Copy root mean square error and paste over here. Control C, Control V, and there we go. And at the moment, this one is the best model. But at the end, you can use any of these models because they are pretty close, you know, the values. All of them are approximately the same. They are providing the same value. But the best is this one, the exponential for the geometric anisotropy. Then in this case, we are going to assume a specific direction, that is the direction of maximum anisotropy, 30 degrees, and then we can use this model as the best one. Now let's go to see the last script. Then we can close here, and it's going to be the same type of script, but in this case it's going to be the leave one out cross validation for the zonal anisotropy to create the graphs and to plot the values for the root mean square error and etc. Then I'm going to cut this one here, cut, remove these two lines, and save with that name. Paste is going to be number 45. Save. Close. And as I said, you can make a lot of different modifications in the scripts, you know, to have the, for example, the KFold cross validation in the scenario you want. You can make a lot of different modifications. As I said, the number of possible scenarios to calculate the cross validation, it's a lot, okay? Every scenario is different. And here I provide you around 5 scripts where you can create different graphs, but you can make all the modifications you want, okay? And the last thing I want to show you is, as we saw these results, that they look pretty bad, the model, you know, because the difference between the real value with the predicted value, it's 811 ppm, and that's a lot. I'm going to show you that even when we are using this model, that this model is this one over here, when we're using this model to create the Kriging interpolation, the final result is not going to be that bad. Then we are going to make the interpolation for this model, for the spherical one for the omnidirectional experimental semivariogram, and we are going to see that the result it's pretty good. Then to do that one, let's go here. Remember that this lesson is not about the Kriging interpolation, it's just about the cross validation, but I want to show you the final result. Then I have here Kriging. It's going to be ordinary Kriging. The field is going to be the logarithmic with base 10 zinc concentration. Cutoff is 1,500 meters. Lag distance is 100 meters. Nugget is approximately a spherical model. The range is approximately 1,000 meters. Partial seal is approximately 0.01 because the model is going to be fit automatically, okay? And we are going to leave that one by default. The resolution, we want 25 by 25 meters per pixel. And that's it. We are going to cut this one because we want just the area covered by the points. Then I'm going to bring a shape file over here. It's going to be with the shape of the river. Then going to open this one. I have the shape file here. Open, add, and close. Okay, if I take this one out and this one out and the variance out also, you are going to see that this shape file is with the shape of the river, okay? And I'm going to use that shape to cut the Kriging prediction, is this file over here. Then I'm going to go to raster, extraction, clip raster by mask layer. Then the input is going to be the Kriging prediction, and the mask is going to be the river. And I'm going to leave all the rest of parameters by default, then run. Process is finished. Then we can remove this one here. Remove, okay. It's not covering all the area because we don't have data points over here. If I put the points, you're going to see that the raster related with the Kriging interpolation is just where we have points, okay? There is no extrapolation, it's interpolation, okay? Then I'm going to take this one out, and I'm going to change the colors for the Kriging interpolation. Properties is this one. I like this ramp of colors, equal intervals, but I'm going to invert this one. And 10 classes is good. And the legend, I don't like this one. You know, I don't like this. I prefer for each color the range. Okay. And apply. And okay. And that's the interpolation. Remember that the value where we have the anomaly, if we can call anomaly, is this one over here. But now if we click on the raster, now we can see for each pixel what is the value, okay? Then remember that the real value, it was 1060, but now we can check for the pixels, the value for the pixel, right? And this value for the pixels is in base 10 for the logarithmic concentration. Then for the logarithmic concentration in base 10, the value, the real one, is 3.025, okay? And the final model, it provides, for example, here a value of 2.78. Here we have a value of 2.85. Here we have a value of 2.80, 2.84, 2.81. As you can see, the values are not that bad, okay? They are pretty, the model it's pretty good. Remember that in this case, what we want for the final Kriging interpolation map is to remove the transformation and put the values for each pixel just in ppm, the concentrations in ppm, not in logarithmic base 10 ppm, okay? We have to remove that transformation. But we did already a lesson on my YouTube channel. I'm going to show you the lesson now. Just go to YouTube, Geo RGB. Then in this video over here, this one over here, I show you how you can change, right, the transformation. Remove the transformation from the raster. Okay, that's it for today. Thank you very much for watching the video. I know it's a very long lesson. Hopefully I speak about all the important things. It was a lot of things. I believe everything is in the lesson. And well, if you have any question, just let me know. See you on the next lesson.